Today we are going to discuss about an important topic of chemistry, or you can say the biochemistry, that is buffer. So what is buffer? Buffer is a solution that resists any change in the pH when you are adding either a small amount of H plus or the OH negative ions. Means if you are adding a strong acid or the strong base, it should resist any change in its pH. So typical buffer basically composed of the weak acid or conjugate base and weak base or conjugate acid. So buffer is of two types. One is the acidic buffer, that is composed of weak acid and conjugate base, and a basic buffer that is composed of a weak base and a conjugate acid. The examples of the acidic buffer, if you talk about, is the CH3COOH, which will work as the weak acid, and the acetate ions that will work as conjugate base. Similarly, for the phosphate buffer, NaH2PO4 will work as a weak acid, and the conjugate base, it will work as a conjugate base, Na2HPO4, because you can see the number of H plus ions is more in the NaH2PO4, so it will work as a weak acid. Now, if you see the basic buffer, the examples of the basic buffer is the ammonia, that will work as a weak base, and its conjugate acid, which is the ammonium ions. Now, to make a buffer solution, you need to have a knowledge about the Henderson equation. So, this is the Henderson equation. By using this equation, you can make any kind of buffer. So, for example, pH is equal to pKa plus log, this is A negative divided by HA, where what is A negative is a conjugate base, what is HA, which is weak acid. Similarly, what is VH plus, this is conjugate acid, what is B, this is weak base. Okay, so this is an example of the Henderson equation. One more thing is, any strong acid or a strong base, they will have very high value of Ka, and because pKa is equal to minus log Ka, so any strong acid or a strong base will have high Ka, which is the acid dissociation constant of acid, and the Kb, this is the dissociation constant of the base. They will have high Ka and Kb value, and they will have less pKb value. Okay, so this thing you need to remember. And one more thing which you have to know is Ka into Kb is equal to Kw, which is the dissociation constant of water, and it is equal to P 1 into 10 to the raised power minus 14. Okay, so these are some equations which you need to remember as well as understand. If suppose Ka value is given very high, it means the acid is very strong acid. Okay. So now coming to how you can make a phosphate buffer, which is the PBS solution of 7.4 by using this pH. So you can say the pH you want is 7.4, and acid dissociation constant of this buffer is 7.2, which is given. Then you can calculate which is A negative by HA, and what is A negative? This is the conjugate base, and conjugate base is Na2HPO4, and weak acid is NaH2PO4 because it has more 1H plus ions. So you will have 1.58 part of the Na2HPO4 and 1 part of the NaH2PO4 to make a buffer solution that has the pH of 7.4. If in this buffer solution, if you will add any small amount of acid or base, it will resist any dramatical change in the pH. So now if you see how, why I am saying is, suppose if you are having an example of NaH2PO4 which is a weak acid, and Na2HPO4 which is a, let's say, conjugate base. This is the conjugate base and this is the weak acid. As I said, it has one H plus ions more. Let's say if this is 0.042 and this is 0.058 moles. Okay, so what will happen if you calculate the pH of this solution, which will be equal to pKa plus log 0.058, which is the conjugate base, divided by 0.042. So if you will calculate, the pH will come around 7. Okay, now you are adding the, suppose, 0.010 molar of NaOH. So what you are expecting basically, you can also write this 10 to the power minus 2. So POH is equal to minus log OH, which is equal to minus log 10 to the power minus 2, which is equal to 2. So if you will calculate the pH, it should be pH plus POH is equal to 14. So pH plus 2 equal to 14. So pH, it should be equal to 12. So if this is not the buffer solution, then if you are adding the 0.010 molar NaOH, then in that case its pH will change, should change dramatically to 12, but it didn't happen. Why it is so? When you are adding, one more thing which you need to remember, the base, if you are adding the base, that will always react with the conjugate weak acid, and if you are adding the acid, that will always react with the weak base. That is the fundamental rules of this. Okay, so here you are adding the conjugate, here you are adding the NaOH, which is the base. So it should react with the acid. And what is the acid here? It should react with this particular solution. This is the weak acid. So what will happen? This amount is going to be reduced by 0.010, and this amount is going to be increased by 0.010. So when you will do this calculation, you will see, now if you will calculate the pH, so now if you will calculate the pH here, if I write here, so pH is equal to pKa plus log conjugate base, which is 0.068, and 0. weak acid, which is 0.032, because this will become 0.032 and this will become 0.068. Now if you will calculate the pH at the pKa of this buffer, then it will be around 7.2. So instead of 12, the pH is only changed to 7.2. So that is the reason this particular solution, NaH2PO4 and Na2HPO4, that works like a buffer, because it resists any change in the buffers in the pH. So that is the thing. But this thing you always remember, whenever you are adding the strong base, that will react with the weak acid. Whenever you are adding the strong acid, that will react with the weak base. So that you have to remember. So whenever you are adding the strong base, it will react with the weak acid, so this amount is going to be reduced. Okay, for example here, because this is the strong base, it will react with the weak acid and the concentration which is in the molarity, not in the moles. Okay, so that is going to be decreased by whatever the NaOH you are adding. Okay, so you can also calculate how much is going to be the ionization, percentage ionization. For example, if you are adding the HF and this is the H2O and this is the liquid basically, so liquid we will not consider in the equation, then you will be having H3O positive and F negative. So this is the ionization of HF when you are adding the water in it. So suppose here if this is 0.075, then this is basically 0. But let's say it become X, which you do not know, then it will become 0.075 minus X. Okay, so in that case, what you are going to do, you can calculate the acid dissociation constant, which is equal to H3O positive F negative divided by HF, and suppose this is given like 7.2 into 10 to the power minus 11. You can see minus 11 and Ka is very less, it means it's a very weak acid. Okay, because for the strong acid the value of Ka is very high, so this is going to be X and this is 0.075 minus X. Okay, so because this is a weak acid, this X you can ignore, ionization will be very less. So in this case you can see X square divided by 0.075, and you can calculate the X, which will be like 0.028, something like that it will come. Then you can calculate the percentage, how much is the HF is going to be ionized. It is going to be, if you are adding, if the initial concentration is 0.075 moles, it is going to be ionized by 0.028 by the total initial volume into 100. So this is the percentage ionization of the HF. Like this you can calculate. Now if we say like you have 0.2 moles of HCl and 0.6 moles of H2SO4 in, let's say this is in 2 liter, this is in 1 liter. Can you calculate when you are adding both of these how much the pH is going to be of your solution? So in that case you need to calculate the moles. So how will you calculate the moles, which is 0.2 then molarity, which is 0.2, then that is volume, this is 2, and H plus ions, which is 1. So number of H plus moles is equal to molarity into volume into H plus ions. Similarly for this it is 0.6, which is molarity, then volume, which is 1, right, and H plus ions, which is 2. So number of H plus moles, if you see in the HCl, will be HCl may in this it is going to be 0.4 moles. Then you can calculate H plus moles in H2SO4. It is going to be 1.2 moles. The total number of moles is going to be 1.6 moles. Okay, so molarity will be, you know, the what is the molarity? Molarity is moles divided by volume. So molarity is equal to be 1.6 moles divided by 2 plus 1, which is total volume, and you can see this is like this. So you can say 0.5 moles is molarity is going to be the solution. Now you can calculate the pH. So pH is going to be minus log 0.5. So this is going to be the pH of the solution if you are having 0.2 moles of HCl and 0.6 mole of H2SO4 if you are adding in the solution. Okay, so in this you need to calculate the number of H plus moles in HCl and H2SO4, calculate the total number of moles divided by the volume, and that's how you can calculate the, you will get the molarity, and then you can calculate the molarity is in the form of H plus ions, so you will get the pH. So this is the pH of your final solution if you are adding all together like this in your solution. Let's say if we are having 0.2 moles of HCl in 2 liter and you are adding 0.8 moles of NaOH. Let's say in 3 liter. What will happen in the, here also you need to calculate the number of H plus moles, which is equal to 0.2 into 2, which is molarity, volume, and number of H plus ion. Similarly here 0.8 into 3 into OH ion, which is this much. So if you will see here, it will be 0.4 moles of H plus, and here it will be 2.4 moles of OH negative. But now this base will react with the acid. Okay, so what will happen? This particular thing is going to be reduced, and this, so in this case so this is like, let's say the example I have given is basically, so this is going to be 0, and because OH is very high, which is 0.8 moles, so 0.4 this will react with this. The example I am giving is very, numbers I have taken is very wrong, so you will be getting, we can basically erase it and make it and here also we can erase it. And let's do it one. So here you will get 0.3. okay, so it will reduce by 0.3, which is 0.1, and here you will get this one is 0.1 and 0.1. So you can calculate the pH of the solution, that is going to be total number of moles is going to be 0.1, which is going to be formed, and this is water, so we will just cancel it. So you will be getting number of moles of NaCl, which is 0.1 divided by total volume, which is 5. So you will be getting 0.02. So you can calculate the pH, which is equal to minus log 0.02. So basically the rule which I want to tell you, if suppose any base is given, then that is going to react with the acid, so that the acid concentration is going to be reduced. The H plus moles, if it is 0.4 and OH moles is going to be 0.3 moles, so you will get only the final product is going to be only the 0.1 moles. So 0.1 moles divided by the total volume, which is, let's say here it is 3 plus 2 5, so it will be this, and then you can calculate the pH, because this is the H plus molarity, so you can calculate. So the pH is the final solution, the final pH of your solution is going to be like this if you are adding HCl and NaOH. So that's what something which I want to tell you. Before I said 0.8, if you are adding this much, then you will not get at any product basically, okay, because 0.4 minus 2.4 is negative, so you will not get anything here. So that is why I changed the number from 0.8 to 0.1. Okay, now coming to the titration, histidine titration, which is I just want to tell you because there are so many questions asked in the exams on this. This is the histidine. When the pKa is 1.87, it will lose H plus ions from here. When pKa is 6, it will again lose one H plus ions from here. And when the pKa is 9.16 or something, 9.17, then it will lose the H plus ions from here. So at the pH of 6, you will get this particular thing which is more. At the pH of 9.17, this particular thing which you are going to get it more in comparison to this. Here if you see the charge, this is plus 1 minus 1, which is 0. So this is the Zwitter ion. It will not move towards any electrode, means neither to cathode nor to anode, because its net negative charge is 0. But here if you see the net negative charge is plus 1. Here if you will see the net charge is negative 1. So accordingly they will move. So cathode has the negative charge, so it will move towards cathode. This has the positive charge, so it will move towards anode. So here this is the titration curve, and you can see at which pKa value what particular form is going to be in the more concentration. For example, at pKa of 6, you will see this particular thing, Zwitter ion, is in the more concentration, which is always in the molarity. Similarly, in case of the 9.17, you will get this particular form of the histidine in the majority of the form, which is this one, and this form will move towards anode because anode has a positive charge, right? So that's all about today's lecture. Thank you so much.